Hi everybody and welcome. In this video, I'm going to share the presentations of the third iteration of the Generative AI Music Workshop that I organized in conjunction with Music Technology Group. The workshop was held in December 2024. In the presentation, you'll see all the different teams basically presenting what they've done throughout the week of the workshop and also letting people understand a little bit what was behind the performances that they showcased the day before during the concert. Oh yeah, there was a concert, and if you haven't watched the concert of that workshop, I suggest you go check that one out because it will give you a lot of context, and I'm going to put the video link up here. That's all on my end. I'll leave you with the presentation. I hope you enjoyed them.
Cool. Hi. So what we've been trying to build this week is a kind of a live composition assistant, and the idea behind that being we have played with tools where they're like drum samplers and they can chuck out like random patterns or random sets of instruments and patterns, and you can iterate through that by kind of selecting which layers you want to change. And so we thought we would extend that to multi-track kind of a composition assistant that in theory was going to work in real time, but didn't quite. So, do you want to talk to this?
Sure. Yeah.
Hello? Okay. So the idea was to create an EDM kind of live performance environment, also for composition, but also for live performance, that can AI create new MIDI of a chosen musical element based on previous material. So as if we were explaining this to our grandmother was the instruction. The idea is that generally you have 4 streams of music elements, the drums, the bass, and the harmony, that we feed into the model, and that the model we get to choose will return one of these elements for us to then play as the next section of the next song. So this is what it looks like in Ableton. For those of you who are not familiar with Ableton, this is sort of the 4 streams or tracks that will generate a MIDI clip, and this is the anatomy of a MIDI clip, which is the symbolic representation that you can send to any synthesizer or drum rack.
You guys want to talk about this part?
So we dug around a lot in the material for how to do this, and there are Google Magenta provided a way of doing it for 3 tracks a number of years ago using RNNs, and then this is a bit too technical for my grandma. Yeah, so we found Valeria basically pointed us in the direction of a useful machine learning model that was released last year that could help us do this. So it's called the Anticipatory Music Transformer. So we basically tried to implement that over the last few days, and using ChatGPT, this is using AI to produce a diagram of how it works. It's kind of typical of how we feel about the process because this is completely incomprehensible. So this is kind of what it feels like to us, but actually what is happening is just within Ableton Live, we have a Max for Live patch, and that calls out to a Python server that's hosting this model, and it pulls out the kind of pitch and note information from each of the 4 tracks that we've got, and encodes, passes that, packages it up, sends it to our Python server and asks the model to generate new MIDI based on that context. And so the idea being that like if we want to refresh the lead or the chords, we send everything, and then it will only refresh the lead or the chords based on the other musical context and give us something musically coherent in theory. Yeah.
Yeah, I can do that.
Nice.
So I guess, Chris got into a little bit of the limitation is right now we can just generate one at a time. I think the future idea is just like we could extend it to add like all the layers or multiple layers that we want, keeping one, or even saying, okay, start over from scratch and then just generate a new set altogether. And right now it's also limited to a bunch of instruments with MIDI, so we've kind of mapped it into a 1 instrument per track. I think adding more instruments and mapping that would be a good idea as well. I think towards the end we did get the temperature control to the plugin though, right? So I think this is not a future idea anymore. This is we can go between mild and wild. Is
Yeah.
that still?
It's a now edition. Yeah.
And I think the final last thing is like we kind of relying on just one model for everything. And I think with the initial investigation we were doing, we kind of saw different results for different set of for different kind of input that we want. Like so, for example, like for drums specifically, Magenta when we were testing actually gave us a pretty good results for drums using drums RNN. But like I guess we could try to play around what we're trying to extract. Could be from a different model depending on what input we give it. And I guess we can do instead of the video we can do a demo.
We can skip that.
All right, so as you can see,
As you can see, we're just playing it here, and I mean, pay attention here to the terminal. And then I'm just going to reset this. And so we can choose either drums, bass, harmony, or melody. I'm just going to... So we're actually going to now... we're just going to choose melody. Right, we have this arc melody here.
so of course the best part about this
So it's going. So it's currently generating it locally. We originally were trying, because it takes a bit of time, we were trying to do it real time. We were trying to host it somewhere else to run it on a GPU. And we could do it, get it to do that, but it would run in a couple of seconds, which is good for a live situation, but it would just try to check out garbage.
now we have the next one. So now it's already generated it. So it generated a melody that works really well, actually. And that's how it works. Generated melody works really well. Okay. So, none of this works. Hello, none of this works. Oh, anyway. Can I do another one? All right. Let's see what it does. I'm gonna play it. Got it? Just got it. Yeah, there you go. Cool. Yeah. So you can see
So
the
the idea behind this model is that it's a kind of iterative composition helper, and the idea is that you prompt it with your starting melodies or chords or whatever it is, and you then ask it to help fill in other bits, and you kind of go back and iterate. And so that's kind of what we're trying to build in Ableton here. It's just a bit slower than we wanted it to be, but there we go.
Sweet. We are Binary Star, Valerio, and me, Ankit. And we decided, or we had a conversation and a nice chat early on Monday, and we decided to build an generative audio performance assistant of sorts using primarily Rave and MLBs to control timbre transfer and sound manipulation in real time. So our goal was to have a real-time system. And what did we do? We created a couple of systems. So I was largely in charge of dealing with the percussion aspect of the entire project, and I can get a quick demo. So this is the raw sound from the drum machine. And this is the timbre transfer sound. So that's basically the drum or percussion part of the project, and Valerio will take over for the voice one.
Yes, an example for start. Yeah, here are the two block diagrams of this is my block diagram about the vocal synthesis part generation, and this is the other one for the drum machines. And here we have a first stage dedicated to the symbolic part, to the control of the sound synthesis, and here we have a multi-layer perceptron regressor mapping a two-dimensional parameter space to a 10-dimensional parameter space. First 8 parameters are controlling the sound generation stage, where we have two traditional synthesizer, like a vocal synthesis. The algorithm is named phase aligned format generation by Miller packet, and with a format control. The last two parameters are controlling another multi-layer perceptron regressor, acting and exploring the latent space of a variational autoencoder, where we fed our sounds into the encoder. The dataset we use is our organs, and that's also something similar for the drums. Yes, this is the patch, the pure data patch. Yeah, so.
Yeah, and for the drums, the signal flow is largely similar. I'm generating symbolic data via the multi-layer perceptron. For my use case, I had 2-dimensional input data, and which was mapped to the 4-dimensional output data required for the latent space exploration of the VAE that I had. I was using a custom model that a friend of mine had trained on drum and breaks, and that model has 4 latent dimensions to explore. And yeah, this is basically how it was set up, and while during the performance I was essentially controlling the MLP parameters in real time. Also, there were some math operations in between the MLP layer and the latent space layer. And the timbre transfer was happening on the sound of the drum machine, which I demonstrated earlier. And yeah, that's pretty much it.
Yeah, so we are the Hive. We made AI to make you cry, but in a good way. Emotional, happy, or however you want to feel crying. There we are. First, we have a short demo video showing our UI tool that hopefully loads. Yes. So you're going to see Francine inputting an audio file of her singing into the tool, which you can then visualize and play back.
Been dragged through the dirt, been ravaged by war.
So it's about a 3-minute clip of just her singing. You can pick, I guess you can read it, but you can pick different moods, different modes, different key, different starting chord, and the number of beats you want to have per chord, so the speed at which new chords come. Then you click Analyze and Generate. It takes about 1 minute, so we skip forward magically.
Been dragged through the dirt, been ravaged by war.
So you get some output with chords and the singing, and if you like it, you can generate it and download a MIDI file with it. So the basic diagram of what we did, again, this is basically what was in the video. We take the input audio, we run some stuff on it, I'll tell you about that later. It outputs a few ideas, and you can pick one, download it as audio or MIDI, and bring it into your project, edit it further. It's designed to be kind of a musician's tool. So the first thing we did was we trained a Markov model to generate chords. We trained 3 different models for different modes. The billboard, that's from a big data set that's available. We assume it has mostly major and minor, so Ionian and Aeolian modes. And then Francine made some, manually made some data sets for Mixolydian and Dorian progressions. and we train the Markov model. It's only in order 1, which means it's only paying attention to one previous chord symbol, so it can get a little lost as it goes, but I think for our purposes it actually worked pretty well. So we take the input audio, just singing, we run some beat tracking on it, which actually is quite difficult because it's only vocals, it doesn't have drums, it doesn't have a lot of harmonic information, but it did okay. But I would say if we want to improve something, that would be a spot where maybe if we take in the full song as input, we can run beat tracking on that and then extract the vocal using some source separation, something like that. We then transcribe the vocals. It's the green line down here. And then we generate chords. So the left side, in green is our inputs, so we get beats per chord, and that looks at the beats estimated, which divides this into kind of windows. Based on the key you choose and the mode, a Markov model is chosen that's kind of has a certain rotation of its transition matrix. And then we're just generating chords, and at each step, the probabilities output by the model are also affected by the pitches that are within that window. So if the model thinks it's an A sharp, but there's no notes down here in the A sharp, then this kind of changes the output probabilities. And the final thing is just an output example of Francine's, where kind of worked pretty well. So she had to change a couple of chords, but yeah, in general we found it to work quite good here. If it loads. Okay. So I can tell you that I think here we go.
Been dragged through the dirt, been ravaged by war, shot at and hated, beaten and scarred.
Skip forward to the chorus. Okay.
My war has been fought and won.
So there you have it. Thank you.
Hello everyone. So this is us, and the idea at the starting idea was to investigate ways to explore the latent space in variational autoencoders in the Rave library through feedback configurations. We'll see a few examples of that. And for the performance, and autoencoders were developed to reduce the system dimensionality and to generate controlled data. So we recorded a short examples of the sounds that were produced. So it's not a recording from the performance for yesterday, it's just to hear how the different sounds change according to the data fed to the configurations.
Oh, it's a bit low. Alright, I guess we'll do that.
Well, I guess you can all go and search for it on YouTube as well. Maybe use headphones if you like. This is the architecture that we developed. Maybe, I don't know.
Okay. So basically we have all the audio is happening through data on 3 instances of Rave, 2 with percussions and 1 with voice. And we have a MIDI controller communicating to Python, basically, that's accessing the latent space of autoencoders that we trained. And so, since those configurations are very complex with tons of parameters, it basically expands the parameters. And so, with very few knobs, we can control a lot of stuff in interesting ways, and much easier to improvise and perform.
Okay. So these are some of the examples of the different configurations. Some were investigated, the others are maybe left for the future. And so feedback configurations were drawn between the outputs of the decoder and the input of the encoders, or these variational encoders in the library, or other like some processing techniques were used, like FM, to vary these feedback configurations, or the position of the feedback configurations were varied, like it was applied, this concept was applied within the latent space, or between the priors, so between the outputs and the inputs of the priors, or between the outputs of the decoders and the inputs of the priors. And then also the rerouting between encoder and decoder were selected, and all configuration were possible via a matrix. And of course, this morning I was starting working on combinations of the configuration seen above. But some of the sounds from the video that you might be listening to later are in there. These are just schemes of the examples. And
we use autoencoders for control data. Basically, PD pitches have a tons of parameters to control. So, what if we want to map parameters to control with only 4 number of knobs? So, basically, we implement a model and with a lattice space of dimension of 4, and with a Python training, and we put the decoder on pure data, and now we have basically we can control all these parameters with only 4 mini knobs on pure data, and we just try to do some experiment, and that. Thank you.
So we made this jazz chord progression generator, where you input chord symbols for an A section, and you give it to the robot, who references its data set of a real book, and then you get some chords back. And Mano's going to tell you a bit about his UI.
So this is a video demo for UI. So basically you input chords there in text format. You get the chords, and we got 2 modes. One, outputting them in score notation. Yeah, it's a and then you can rearrange them and play in the order you like. Basically, it's playing left to right. You do the selection of the chords you want to play. And that's the first mode, and the second mode that we used yesterday in the performance is basically displaying only the name of the chords. So if you would like to play them as you would with iReal Pro or something, just the notation with the chords. And so we got the AI part with a button to generate B section, and it's going to be contrasting with the first chords that you inputted, and that is the B section generated by the AI. And you could also submit the A part again. And now comes the AI. that's basically it. Yeah, so kinda. You could see that it's a pretty simple progression. It likes to do dominance a lot and 2-5-1s, but yeah. So next.
So how do we do it? And that's something Ingrid is going to tell you about.
Yeah, so how we did it is we have this web interface that you saw where we're using basically a text input, so you type in the 8 chords you start with, and this goes to our API, and then we're using the LLM, so the model, to basically look into the real book and see, is there something similar, can we get inspired, and then it also listens to our instructions about the style, or like the relationship between the A section and the B section. And this chord sequence is then returned back to the user via the web interface, and then the humans involved can reorder chords or play them. And yes, this is how we did it.
Yeah. And so, to answer your question, Cartman, what comes next? Future development might entail fine-tuning a model, adding slash chords or cluster chords, hybrid chords, being able to have a user define the data set to get more individualized results in terms of the chords that come out of this system. And also being able to define voicings, if it's supposed to be an open voicing or a closed voicing, and also being able to produce good voice leading.
That's the next part.
Thank you very much.
That's it.
There we go. Cool. Thank you. All right, thank you. So we are Synaesthesia, and yeah, we set out to develop an agent that could help us do sort of an audio-visual performance. You can see here we had some goals originally to have multiple agents that would generate code for a variety of different systems, one being SonicPi, the other being processing, and these would all kind of create an interaction dialogue between hardware and these software systems. So we had some controllers, as some of you saw, they were related OSC messages, and yeah, we can go a bit into this. We want to talk about, you guys want to? Yeah,
yeah. So, initially we had the idea of having a pool of agents dealing with different tasks, so the audio task, the visual task, the mapping to the network configuration. So we wanted this pool of agents. And also we wanted to automate completely the step between the generation and the actual playing. Actually, we had to simplify the architecture for a bunch of reasons. So the assistant in general, I mean, every trial that we did in generating graphical ideas was completely terrible. So in the end, we left only the graphical agent to only program, like generate the interaction and the response of the music to the graphical ideas. That was just one that we generated at the beginning. And the assistant finally were two. So one specialized in generating SonicPi code, which would be compatible with the Ableton-like set that Tolga will talk about later. And another one to generate a random interaction response through OSC from processing. So the two agents generate SonicPi code, but generate also different kind of interaction with processing and Ableton Live. What else important on this side? I think it's okay.
I'll explain to you what you heard yesterday and how we set up the performance. So the code generated by our agent is run in SonicPi, which generates up to 8 channels of audio. Sorry, 8 channels of MIDI, which is sent over to Ableton. And how we set up was we have 2 styles. And if you know Ableton, there are 8 active tracks there. We set up for each style 1 drum track, 1 track for the chords, another track for the bass line, and lastly melody. these were all mapped to my narration controller to be able to just tame some of these sounds because it's somewhat random. So style 1 was hip hop, and we had performance controls for individual levels, and just for further flexibility and because of the randomness, we wanted to land on some unique grooves. I mapped the pitch function in Ableton, which would pitch the drum rack by a few semitones, and how this works in Ableton was a bunch of notes would land on this drum rack, and I have created rows of kicks, 808s, and effects, so by pitching with this MIDI effect, we would land on unique grooves. Similarly, we prompted to change the style. We started off with an ambient, and secondly, like a 90 BPM hip-hop track, and lastly, we moved on to something like 140 BPM industrial-inspired track, which was sent to my Electron device, which also had drums, and I would also pitch that from time to time just to generate unique grooves and some master effects for performing.
So for which concern the way how agents were done, basically, we talked a little bit. Yeah. No, just like I wanted to highlight how we identified the fine-tuning as the best possible approach for this. So give a data set of kind of labeled question-answer about generate code on some style. But of course, it was not feasible to create a dataset in this time, and also we will have the computational time limits during this workshop. So we finally went for a RAG, retrieval augmented generation approach, and let's say also an advanced system prompting approach, and which was much lighter. Okay, yeah, we are okay. I think we told more or less all. Just that the graphical changes that you were seeing originally came also from the mono device. So through the graphical change of the mono device, actually was also the video were talking to music and changing music parameters also. Okay, I think we finished time, so I don't know. Thank you very much.
Thanks. So this is our project. So this is the algorithm for what we did for generating melodies, but I'll play video while I explain it. Basically, you can have, just press me. Basically, you can start either with a seed, or you have, or you start scratch, then you press different buttons to like add things to extend the melody, so you end up with something like this. And yeah, we extend it like 2 bars at a time. You can also like repeat previous things or upload a new phrase. And you can press a button to download the MIDI and play around with it in your own space, or press a download or generate accompaniment button, and it'll generate one, which we'll see in the next slide. Yeah, so it takes about like a minute or so to generate it, so just play a little bit of it. So you get the idea. Cool. So yeah, this was like an app we made in Next.js plus Flask. It's on GitHub, like I have the link in there if you want to play around with it. We modified the Markov generator a little bit to handle various things and to extend the sequence. Also the accompaniment was using like a music transformer, and I put links to that if you want to play with that too. We had different experiments that we didn't show in the demo, but like using a variational autoencoder to like make similar sounding melodies, or doing varying like the order of the Markov chain to control things a little bit better. I'll pass it off to you. Yeah.
So I will just roughly mention the data we used for Turkish makam side. So we use the data from this CMTR dataset, the text-based collection of machine-readable symbolic scores for specifically for Turkish makam music. We picked Hijaz makam, which was suggested by our musician in the team, and like there are some statistics there. The thing is, yeah, we read this text file, converted it to Music 21 format that it can process, and then we made an output of the result as MIDI by adding microtones for that. So that's why it gave the taste of makam. So yeah, that's all I wanted to mention, and Vivek will continue now.
So we have a Hindustani melody generator and a Kumpia melody generator. So for the Hindustani one, I used just one composition, which is in Rag Bihag. Hindustani music is basically like constrained, and I think like one song is enough to capture the essence of it. So just one song was used for the Hindustani part. I think you listened to it yesterday. So I will just play the Kumpia one. For Kumpia one, my friend Carlos, who is in the SMC, suggested some songs. He sent me some MIDI files, like 11 songs. And play that one.
Hello everyone, we're with WavePlay. We're going to show you what we played yesterday. Okay, so the initial idea was basically to enhance a collaborative project by JP called LocomIA with AI, and what we wanted to do was use a model called MIDI emotion to basically generate melodies based on two parameters, balance and arousal, so basically mapping your emotions to a melody. And we also wanted to create the drum sounds using stable audio open. So we faced many issues when we tried to implement this idea, and the main issue we had was that the MIDI emotion trained model was really slow when it comes to inference. So we couldn't do it in real time, which was what we intended to do. And also the model creates many tracks, like for drums, for violins. So we also had to extract a melody from all that data. And we also had a lack of control, so we wanted to also control what we generated, which was challenging. And we also had to adapt to what JP designed. So we basically had to fit all the data generated into 16 time slots, which was really, really challenging.
Okay, so today JP and Santia have implemented drum sample generation with a stable audio open with a text prompt to integrate in GP application. How have we solved all of these issues? So we have made a backup MIDI files with all the combination that we needed, with more than 100 combination and with 105. And as well, we have made some post-processing to get the melody, and as well to adapt the MIDI files to the 16 time slot.
Well, this is more or less the architecture, yeah, I think we have time. So the sequencer, which is a collaborative sequencer, can be embedded in Ableton Live, so you can play with other instruments, you can dab with it. And the application on one hand requests melodies that we generate like a cache, as Luis explained, and on the other hand, it would call the stable audio open API, which Satya helped us develop, and incorporate those samples into the application. And everything is coordinated in the backend by a Node.js server, which also connects with all of the participants. This is the final interface that we created for the melody. So you would click one of these buttons to indicate your emotion, and it will generate a melody that reflects that. And here we couldn't show it yesterday, but hopefully we can make it work real quick today. Here we have a So this is the default sample sound, and if I enter a prompt, so that way you can have multiple participants using their own sound and entering their own sound with using prompts. For future work, we need to scale the backend because it's currently just a model generating the sample. So if you want multiple people doing it at the same time, we need to find ways to scale it. And that's it. Thank you so much.
Okay, the name is just a native Spanish band that had IA in it. It has nothing else to do with AI. The choir, you'll see why. Okay. The architecture, we had a random walk generator. Well, it's not a generator, it's just a random walk in Super Collider that plays a degree in the scale, in a minor scale, and then from inside Super Collider, for each note, it generates a chord according to the Tintinabuli rules, which is a compositional system by ApplePie. Then those 4 notes in the chord are sent to some agents through OSC. The drawing is not faithful. It has 4 different OSC messages, not 1 divided in 4. And then we had 4 models, Rave models, playing in 3 different machines. 1 in Max MSP, 1 in Super Collider in a different machine, and then 2 in Mercury live coding language, which was interfaced with Flock, which is a shared, independent, multiple cursor editor that allows multiple users to edit the same code at the same time, and then that sends the messages to, that controls the Mercury agents.
So really quick, we use to create the sound, we use Rave, we train 2 models using a dataset. Choir dataset is the Smook choir. If you know Smook, it's a music school that is also that is here in Barcelona. And we use a pre-trained model trained from Jack Armitage from the Music Instruments Lab in Reykjavik. And we train this, and for playing, for the different sounds, we use the different models, like an under-trained model for the most noisy part, and a better trained model for the most precise part. So we were able to select the timbre that we were working. And we also trained another model in After that Laura is going to talk about a bit.
Yes, so we also experimented a bit with After, which is also a generative model from LocomIA. It's very new, so the real-time implementation is a bit limited. We played a bit with one of the pre-trained models they provide, which is real-time, and then we also trained a model with the same dataset, but this one was not real-time, so in the end we ended up using it.
What we did for the performance then was to use these different systems that Roger said before. Their Super Collider, we use Rate in Super Collider in MaxMSP with a library that probably you already know. And then the other thing I did was to create a synthesizer that is now embedded in Mercury, which is a live coding language. That happens that runs with MaxMSP, so it wasn't that complicated, but I added that, and then that made possible to make this type of sounds. Also, yeah, play more with rhythmics and with different, I don't know, synchronizations of things. I don't know if that's gonna work. Those things you heard yesterday. And then the other thing that that we used was that flock thing. Is that environment that you can also use to perform together. So we use that with Roger. So both we're using the same code to send messages to Mercury. And very important, this was our score for yesterday. So yeah, that was pretty much what we did in 9 minutes. And we put this amazing name also because we are very good with names. That's it. Thank you so much.